In Practical 5 today, we're going to use Blue Canoe to examine, first of all, more sophisticated visualization of model results. So we're going to do things like sync 1 and 2D views, extract and plot velocity raises, look at residual currents, shear stress maps, and then we're going to compute and plot sediment mobility. And then in the second part, we will compare two model runs. But let's look at more sophisticated results, and we are going to use the georectified image from day 4, and we're going to use the results that we also generated in day 3. So again, my computer is slow. Let's just wait for it to wake up. Okay, rather than open, I wanted to import georectified TIFF from day 4. There it is. And I'll bring it in here. Okay, and then we're also going to open our results files from the Southampton real simulation. Okay, like before, we'll drag in the U and V velocity, animate that, and I'm just going to scale it to 900, so the vectors aren't completely overwhelming. Okay, now what we're going to do is create a point somewhere in the model domain. So let's just zoom in here. Zoom in. Okay, and we'll create a point using the new point set. I'm just going to create a point in the middle here. Click on that again. Let's call it EG understroke 0.1. Okay. Now what we can do is extract time series at that point. So go to free surface like we've done before in day 4, tools, extract time series at multiple points. Click OK. And again, we can look at that in a one-dimensional plot. So here's our water levels at that point. And here is our flow vectors at that point. Our flow vectors across the domain. Okay, now what we're going to do is sync these two views so that as we animate one, the other one animates as well. And this will allow us to say, for example, look at the vectors at high tide, low tide, peak ebb and peak flood is normally what you want to use. So select the 1D view to start with, click on View in your menu, then select Sync. And we've only got one other plot open, which is a 2D, so we'll click that. Now what that red line means is that that's the time that we're currently viewing these vectors. So if we go back to the 2D view and zoom back and forward, what we should see is this red line moves in time. So for example, here we're at low water, we could stop it there, or we could continue through. So this is just a nice way for you to kind of, if you wanted to plot just at the flood, so for example we stop here, this is at the flood, and we can continue logging on there. So that's a nice way of syncing views. Now what we're going to do is extract and plot a velocity rose. The velocity rose gives you very succinct information of how currents, speed and direction are at a particular time or location. So what we can do now is go to Velocity UV, click on Tools, Extract Time Series at multiple points. Select our single point that we've chosen there, and this will now select U and V at that point. Now if we right click, we can go Extract Velocity Rows, and we can choose information here that we want. But what we'll do is we'll leave everything as default and just press OK. Now what we need is a new polar view plot, and it's this one up here is the polar view plot. So we'll click that, and now we can drag this onto the polar view, and there is our current vector. So you can see at this particular point, as you might expect, the currents are dominated by two directions, and you can see the speeds up to 1.5 meters per second. Now what we can do is create it at more points and compare. I'm not going to do that, but you can easily just extract more points, follow the same procedure, and then you could look at, for example, on this side, that you'd expect the currents to go in a different direction. Okay, what we're going to do now is look at residual currents. Now essentially a residual current is the mean current over a particular period of time, say a tidal cycle or several tidal cycles. Residual currents are important because they can influence sediment transport and the morphological evolution of estuaries. Because the tide in Southampton is complex and very asymmetrical, much longer flood than ebb, this can be an important factor in the residual current and hence sediment transport. So what we're going to do to start with is click on U and V velocity, Tools, and Extract Residuals. Now here is the time step over which we want. Now I'm going to start on time step 49, which basically is the 2nd of January, so 1 day later, to get rid of this 1 day warm-up period. And I'm going to go to 1393, which is exactly the same point in the tidal cycle, and this period basically covers an exact spring tidal cycle. Both of these are at high water. So if we press OK, we can see it doing some calculations now, and there's that residual there. What we can do is a new 2D plot. Let's drag on our rectified image. Maximize this. Drag on our rectified image. There we go. Drag on our residuals, and this now shows us the direction of residual flow. And again, we can scale this to make it a bit more sensible, so it's not horrible. Let's try 2000, that might be a bit small. But now we can see the kind of directions of the... So what I'm going to do is just zoom in here, and you can see that the residual flow is going one way down this Isle of Wight, that way. So it sort of shows you that sediment transport might be expected to go in these directions. And what you could do, for example, is to validate your model, you can compare this against ones on the SCOPAC website. Okay, now what we're going to do is calculate shear stress maps, and this is kind of a measure of the friction caused by the water acting on the bed. And again, this is important because it affects sediment transport and sediment movement. For a fluid to begin transporting sediment at rest on the surface, the bed shear stress must be exceeded, so it's critical shear stress. Now what we do, like before, it's very easy. Click on the velocity, go Tools, Extract Bed Tools, and here we can compute shear stress map from current. So shear stress is related to current speed. Let's put in our temperature like we did previously as 9. Salinity at 30, but again, when you do this for your assignment, put in realistic ones there. We'll leave everything else as default here and compute it. And we'll save it in day 5. I haven't got a day 5 folder, so I'll just create one quickly. We'll save it there. Okay, now that's computing, so it's computing it for every time step, that's why it takes a little bit of time. Okay, so what we can do is create a new 2D view, bring in our rectified image, bring in our shear stress maps, like we've done lots of times before, animate, and now we can step forward. And this essentially shows you where the shear stress is strongest. And as you might expect, it's proportional to the current speed, so where we're getting the very fast currents. But using these shear stress maps, we can look at how likely it is that sediment might be moved. Now, I typically prefer to plot these as contour plots because it just makes more sense to me. So what we can do is double click on this or right click and go properties, and in the display here we can go filled contours. We can change this color scale here. So for example, at the moment we're going 0. At that we can show the color scale and go apply. So here for example now you can see the shear stress at different times. So this is probably coming up to flood time now. You can see where the shear is strong, that's likely to move sediments. Okay, finally in this part we're going to look at sediment mobility maps, and they basically give you a feel for spatially over the area. If you had a certain type of sediment, what is the likelihood of it moving? If you have a value of between 0 and 1, this suggests there'll be no sediment movement. 1 to 8 is saltation, greater than 8 is the material is going to be suspended. And again, it's very easy to do like we did before. Click on Velocity U and V, Tools, Bed Tools, Compute Mobility Map. So we'll put these in like we did before, 90 and 30, and here we can put in a certain type of sediment. We can either go user defined or find sands. And when you do your field work and collect data on Bramble Bank, you'll need to put in realistic sediment types here. So again, we can go compute, save that in day 5, and then we can plot this. Let's do a new 2D view, bring in our rectified image, and now bring in our mobility map. Now with the mobility map, what we want to do is again put filled contours, and this time I'm going to change the color scale at being 1 to 8. So I'll put minimum 0, 1, and I can apply that. Now let's just animate this, and we can step through it this for different times. Put on the colour scale just to check. Now for some reason I'm not getting any results, so I'm just going to try that again. Click on Velocity UMB, Tools, Bed Tools, Compute Mobility Map. Just check that I put in all of the correct information. Fine sand, compute, overwrite this. I'm just going to remove this one, bring in our new one, right click, animate, step through. Okay, this looks better. I don't know what I did the first time. Double click, change to filled contours, turn on this color scale, and let's go from 0 to 8 because those are the scales. So here you can see that, yeah, most of this material, if it was fine sands, would be moved here. In this area, it wouldn't be moved. So this is a good way of, in your assignment, looking at whether the changes you make will move the sediment or not. Okay, and that is the end of the first part of